if we think about two cars, we would expect that if I increase the price of car 1, the direct demand should go down for car 1, so we have a negative own price derivative. But some of the consumers who now don't buy car 1 will instead buy car 2, so the demand of car 2 should go up if I increase the price of car 1. So we have a positive cross price derivative. Whenever two products have positive cross price derivatives, we say they are substitutes. So one car is a substitute for the other car. However, there are also products that are complements where we would have a negative cross price derivative. So one example would be a video game console and a video game. If I increase the price of the video game console, fewer people buy this console, but that also means that fewer people buy the video games of this console. So these two products are complements. So one could try to estimate cross-price derivatives or own price derivatives, for example, using market experiments or also using discrete choice experiments, as we will explain later. Often, however, empirical studies don't present the price derivatives, but they report price elasticities instead. They approximate by how much percent the demand changes if a price changes by 1%. So the own price elasticity of product J is just given by the derivative, the own price derivative multiplied by the price divided by the amount sold. And we have a similar formula for cross price elasticities. And since price elasticities measure percentage changes, they are much easier to compare between products than if we would directly compare price derivatives. If we run a discrete choice experiment and estimate the utility functions, we can in principle derive demand functions and corresponding price derivatives and elasticities for so-called differentiated products. So these are basically imperfect substitutes. Think of cars. That's a very good example. So how does this work? We have already seen in the R-tutor problem set of chapter 3a that we can aggregate the choice probabilities of many consumers by just taking the average to compute expected market shares for each product. And in general, the choice probabilities and therefore also the market shares depend on the prices and attributes of all products, and not only for those of product J, but also on all other products. So this means from a choice data set, we can estimate market shares of products. However, we typically don't know the total market size. So if we only invite consumers to pick products, we don't know what's the total market size. So if we really want to derive a demand function or price derivatives, we have to make an educated guess about the market size. And if we are willing to make such a guess and assume that the total market size is M, so it's just some number, maybe 1 million units, then the demand for product J can be written just as a product of the market size times the market share Sj. And the own price or a price derivative of the demand of product J with respect to some price Bh, where H could also be J, then we had the own price derivative, then would simply be the market size M times the derivative of the market share Sj with respect to the price. And if we look at price elasticities, nicely this market size M cancels out, so the price elasticities can be computed just by looking how the market shares change in the price. So to compute price elasticities, we don't have to make an assumption on the total market size, which is convenient. That being said, sometimes we have to make an assumption about the market size if we also want to estimate how many consumers don't buy a product at all, but we will discuss this only very briefly at the end of the R-tutor problem set 3b. Now, when we estimate a conditional logic model based on some data from a choice experiment, we make a lot of assumptions. For example, we assume that these random utility shocks are independently drawn for each combination of consumer and product it chooses. And we also specify the particular distributions that they are drawn from a Gumbel distribution. These are very strong assumptions. And whenever we make assumptions in an econometric model, we would like to better understand their consequences. So in particular, when we are interested in estimating price derivatives or cross-price elasticities, we want to know how flexible is our model. Which sort of price derivatives can our model possibly estimate? Is our model able to capture realistic substitutions patterns? Now, for example, we would expect that two sport cars models are closer substitutes than, for example, a sport car and a family car. So if we increase the price of one sport car, it should have a bigger effect on another sport car than on a family car, which probably is bought by completely different consumers. And will our conditional logic model allow for such flexible substitution effects or not? This is what we will explore on the following slides.